On Iceland Air to Copenhagen in August, I paid $500. $500. $500
So
to
no
Denmark.
frills.
No frills. You can't even get food on the flight, right?
But you have
You stop in Reykjavik, right?
Oh, okay.
Okay, good morning everybody. We can start now, right? Okay. Okay, then today we have defense of Professor Phat. He's professor now, although he's just his PhD defense. Okay, Phat, please start.
Thank you, Professor. Please allow me to express my sincere gratitude to the Dissertation Committee. Thank you for providing me an opportunity to present my research here. So today I would like to talk about the channel-line derivative-based Newtonian methods in non-smooth, non-convex optimization and application. This dissertation is supervised by Professor Boris Monokovic. Here is the outline before I moving on to our main results. First, I want to recall what is the Newton method. I need to recall the classical Newton method, and then we will talk about how do we develop Newton methods when we don't have any information of the derivative. That's called channel line Newton method, right? And application to some practical models in machine learning, statistics, economics, something, and further investigation and acknowledgement. Right? Okay, this is the first part of my talk. Is what is the Newton method? Okay, here we consider the equation Fx equals 0, and F here is C1 smooth mapping as a continuous differentiable mapping. And as you know that it's impossible to find exact solution to this equation. It is rarely case to find the exact solution when F is just a linear or quadratic function. We can easily to find. But when F is a polynomial with a higher degree like 5 or 6, or F is not a polynomial, so it's very difficult to find exact solution. So we need to use the Newton method to do this. Just yeah, and somebody will accept them. And then this is the reason why we need to approximate a solution to the equation 1.
Is this like essentially the gradient method in high, when n is bigger than 1? Right? Is that also
Yeah,
right? Okay.
yeah. We can use gradient method, but here we just focus on Newton method because it will higher the convergence, right? Faster than convergence. And the Newton method is one of the most efficient numerical methods for approximating a solution to this equation. And here is the basic idea of the Newton method. So when we want to find the solution of equation, that means we need to find the intersection between the x-axis and the graph of this function, right? This means I will start at x0 and I will sketch the tangent line, and then the tangent line will cut the x-axis at x1, and we continue this process, and we can find the approximate solution to this equation. And here is the the Newton method. So we start x0 and we construct the sequence x case is that in the screen. And Jx here is the Jacobian matrix of f and x. And we have the fact that this algorithm will generate a sequence that will convert to a solution. If we have that the Jacobian matrix and the solution is not singular, and the starting point is close to the solution. That is the classical theorem. And sometimes we can compute the decay as follows. If F have the smaller dimension, so we can easily compute decay as like this. And here is the application to the optimization problem. We will consider the optimization problem like this. And phi here is a time continuously differentiable function, right? And the question is, how do we find an optimal solution by using the Newton method, right? Because we have the necessary condition like radian phi is equal 0, and then we can use Newton method to solve this equation, right? We can do this. And the solution x bar here is we find is only a stationary point, right? And we can guarantee the local optimality of x bar if we have more condition. That is, the hash-sum metric is positive definite. In this case, we can guarantee the solution we find not only a stationary point but also the local minimizer. Right? And sometimes we have the we know that the Newton method is only local convergence. That means that if we start the starting point is not close to the solution. The
Recording in progress.
Sorry about this. If we start the starting point at, and here this condition is equivalent to the metric regularity that's called the Mordovich criteria, right? This is certified for the case the graph of subdifferential phi is closed, right? And this condition is equivalent to the metric regularity. The metric regularity you can see here is just the arrow bound, the kind of arrow bound. You see the left side is very difficult to determine, but we can compute the distance between y and the value of f, right? So we can estimate the value of u to the inverse based on the distance from any point to the value. That is the arrow bound. And this is known as the Mordovich criterion. You can find more about this in the paper of Mordovich in 1993. And we have the fact that the second order subdifferential system had a solution if the subdifferential is metric regular. It's similar to the classical sense. And we have some additional assumption on phi, but we will not talk about more that we recited in our paper in 2022. We need some general convexity on phi, or the phi is a piecewise linear quadratic function, so we can guarantee the second order subdifferential system and a solution. It's not for any function phi, but we need some additional assumption. Right? Okay, we have answered the first question, so now we go to the second question. Do we guarantee the convergence of iterative sequence generalized by our method? Here, our method I recall here. And we consider some cases. The first case we consider is sequence one smooth case. That is the.
I just have a question. So with this, you're saying that you can find like these equations and just get like this iterative method, but it may not be unique.
Yeah, it might not be unique, but we can choose any the direction it can belong to this set.
Okay.
Yeah.
And you can put conversions right.
Yeah. Any point. Yeah, but we need some condition for the function phi. Yeah, here is the function phi here is C11. That is the first case we consider. And this is a very important function, class of function. C11 here means that it's differentiable and the gradient is locally continuous, right? And this a lot of function like the maximum of the second the tri-continuously differentiable and 0. And Moreau envelope of convex function. Moreau envelope is very important function in convex analysis. And Moreau envelope of convex function is C11, not C2, right? And the subproblem in the augmented Lorentz method, augmented Lorentz method is very first order algorithm that is very important in optimization. But to solve the subproblem in augmented Lorentz method, the subproblem is have the code function is C11, and then we can use the Newton method for solving subproblem.
I'm sorry, in the augmented Lagrange method, which function you refer to C11?
Yeah, that the augmented Lorentz method. So when we start at x0 and we have an x1, and x1 will be a solution of the optimization problem, and that optimization problem subproblem will be C11, and then we need to use some order method to find the approximate solution. Right? And in this case, we have the first order derivative information, but we don't have the second order information. Then our method should be like this. And this method have been presented in our work. And we can guarantee the local convergence if we have the condition like the gradient phi x is 0, that it starts stationary point, and the second order subdifferential is positive definite. Here is just we not only get this result, we get more than that. That means we only need the second order subdifferential is non-singular. That means we have the metric regularity, and we can also get the local convergence, but only to the stationary point, not the local optimal solution. But here, because I want to focus on the local optimal solution, so I need this condition. And we can guarantee the convergence rate, that is at least superlinear. And similar to the classical Newton method, we cannot guarantee the global convergence, so we need the global line Newton method. So we need the step size tau k is chosen by a Mikko rule, and then we can get the convergence of this Newton method. Here is our main result. The function phi here is C11, and we suppose that the second order subdifferential is positive definite, and the algorithm to produce a sequence xk such that the value of phi is is decreasing, and if the sequence here it has accumulation point, then we can guarantee the convergence of xk. How do we know when the xk has an accumulation point? This can guarantee if omega here is bounded, right? It's bounded, and then we can guarantee this condition. And then the point here is the local minimizer of phi, and the convergence rate is at least linear. Linear is that defined here, and we can guarantee the superlinear if we have the condition that the gradient is semi-smooth at x bar. And we will compare our method with the semi-smooth Newton method to solve the testing problem. That is the C11 problem. That's not C2, right? And for our method, that is generalized down Newton method, we say the GDNM, and we can find the reside formula for the Newton direction. But for the semi-smooth Newton method, we can only find the Newton direction if we can solve the linear system equation, right? And in this case, we have the comparison between two methods. Like you see, the GDNM will be more efficient than the semi-smooth Newton method, because in this case we can only compute on the vector, right? But we don't have any metric here, so we get a more efficient than generalized semi-smooth Newton method. And as you know, in the main result of us, we need to assume that the second order subdifferential is positive definite, but in some cases it's very hard to guarantee. But here we can modify a little bit. We can choose the direction decay by using the generalized regularized Newton method. But we adding some regularizer here, then we can find the direction D, right? And here we can have more Mueller's assumption. That means we only need the positive semi-definite of this condition, right? The linear convergence is guaranteed if we have the gradient phi is metric regular around the accumulation point. We don't need to assume that the metric regularity or the space. We only need to assume that this is only around the accumulation point. And then we can guarantee the superlinear convergence if we have the gradient phi is semi-smooth at the accumulation point. But you can find more about our main result in our paper in 2023. And here we finished the first case. We consider the case that is C11. But now we consider the case that the function phi may not be smooth, right? Even if first order smooth. Right here, we consider the case of the function phi is rock regular. You see the definition here is very complicated. This function is defined by Polican Rockefeller in 1996. Now you see this definition is difficult, right? But this covers a lot of function in optimization and variational analysis. For example, from regular function, our observation at the beginning, we cannot release 8k by the sequence here is not 8k, exactly 8k, but the 8 hat k. 8 hat k here is the point that is close to 8k. And because why we need to do this? Because you know that the subdifferential may be empty. So if we choose xk and we compute the subdifferential of phi at xk, this set may be empty. But we change a little bit. We choose 8 hat k may be equal to 8k or may be different. Right? That is the idea. Such that the subdifferential here is non-empty, and 8 hat k, v hat k may not be far from xk0. And you can see that if we solidify this inequality, that means x hat k, v hat k can be seen as an approximate projection of xk0 of the graph of subdifferential. And here is some example how to choose the x hat k, v hat k, right? And x hat k here is xk and v hat k here radian phi sk. If phi is equal to 1 smooth, and when proximal mapping can be computed, basically we can choose the proximal mapping x hat k is like this. And when phi represented by the sum of two functions, we can choose x hat k, v hat k like that. I need to talk about this kind of function more carefully. So this kind of function covers a lot of function in machine learning statistics, right? Like lasso problem is belong to this class of functions. It's very important. It's covered a lot, and support vector machine or L0 non-regularized least square problem is very important in machine learning statistics. It covers a lot. And we can guarantee the local convergence to the local optimality condition, local optimality solution if we the solution X bar satisfy the second order sufficient optimality condition in the same lines. Zero belong to subdifferential and has some metric is positive definite, and we can guarantee the convergence rate is superlinear. Right? And we can guarantee the global convergence if we proceed with our generalized license method. Here is application. So the basic lasso problem is in the first application of our method, right? And lasso problem you can see is it can be represented by sum of two functions, right? And we will compare our method with the semi-smooth Newton method, Lorentz method, ADMM, accelerated proximal gradient, or the fast the fit start. Here is our result. You see that in the case that m equal n, our method is efficient, is more efficient than most of the methods that I mentioned, right? And the second application is to consider the box constraint quadratic programming, and then we can use the our method to compare with the just-regan methods. But here we have our method in GDMM, that is generalized Newton method. GRMM is generalized regularized Newton method, and we compare with the just-regan method, and we get in most of cases we have a better efficient than the methods. And the third application is to use our method to solve the fast batch subset selection problems. Right here is a problem like this, and you see that the function is even non-convex, even non-continuous. It's not continuous, but we can use our method to solve this kind of problem. And our numerical experiment showed that our methods behave better than the proximal gradient method for solving a both problem. Right? And you can find more about this in our paper. And here is future investigation. We want to establish the generalized Newton method for solving different programming, and establish the generalized Newton method for solving multi-objective optimization problems, and establish the generalized Newton method for solving bi-level optimization problem. And because our method now is just work very well in the case that with the lower dimension, but in the future we want to work to deal with the higher dimension, so we need to use the established correlate-based stochastic Newton method for solving non-smooth and non-compact automation problems with high dimension and application to some other important classes of models in data science, machine learning, statistics, and related disciplines. And here's our work. Yeah, it's for papers. Our paper to deal with the new generalized Newton method. We consider the case, the C11, rock regular, non-smooth case, the sum of two non-convex functions that we established some Newton method for this kind of problem. Right? And here's another. So the first, I want to say thanks to Professor Morovich, who is my PhD advisor. Without him, I may not be completing the dissertation. So I met him in at the beginning, first time in Vietnam in 2017. He encouraged me to pursue my PhD study in the United States, and at that time I agreed to become his student in Vietnam, and then I applied to West State University. He helped me a lot at the beginning, so I really appreciate his help for my dissertation.
Which city?
Yeah, in Phat. I am from. I live in Ho Chi Minh City, but I met Professor Morovich in Hanoi. It's the capital of my country. Yeah, Ho Chi Minh City like a big city in Vietnam, but Hanoi is the capital city. Yeah. And I met him at the conference related to the variational analysis. And the second person I want to say, but he may the reason why I want to use Zoom because he chose us, but now didn't have any Zoom, so he may not hear. But I want to say thanks to my teacher. He is a mentor in my undergraduate thesis, and also now he can see as a remote advisor for my PhD degree. He helped me a lot. And at the beginning, when I saw my undergraduate student, I just think that I will be just a high school teacher. I just want to go to high school and teach mathematics for high school students. I didn't think that I will come here to study mathematics or pursue my PhD, but he encouraged me to study mathematics and do mathematical research. Yeah, so I would like to say appreciate his help. And my family, so this is my family will not here to see me, but I want to say thank you for them. Without them, I would not be cannot complete my dissertation. And my collaborators, and they here except because Vietnam now, but except that one, only that here. And I want to say thank to all of them. They collaborate to my papers, and not only in the paper or academic activities, but they help me a lot in the real life, daily activities. So I really appreciate that. And the dissertation committee. So I would like to say thanks to all of you. So you spend all of your time, valuable time, to stay here to listen to my my talk, but have some trouble with my Zoom. So I'm really sorry for this. I didn't control this. And it's not your fault.
It's not your fault.
Yeah. And then I will have some present for your for you. This is just some gift that have some characterization of Vietnam. So I hope that you will remember me when I come. I finish my dissertation. So I just give you some gift for my dissertation.
Phat, but you need to get a committee decision. We can consider it like
No, I just give you.
It was a very good talk.
Yeah, but for Professor Morovich, we have more one thing, special thing. Yeah.
Thank you very much, Phat. Thank you. Thanks a lot.
Yeah. So. And I also want to say thanks to the following grant that support my research projects, not only the U.S. National Science Foundation, but also it's some fund in Vietnam. Right? And institution here, Department of Mathematics, West State University. I want to say thanks to all of the faculty members, professors, and staff in the West State University. And Yeah, they help me a lot when I come here and teach me a lot. And Department of Mathematics and Informatics, Ho Chi Minh City, University of Education, Vietnam. This is the school that I used to study to get my bachelor degree. And then I worked there for 1 year, and then I go to the United States. So they support me a lot to encourage me to study in the United States. And thank you for your attention.
Actually, before our starting question session, I would like to mention that Phat presented some of his publications, but it's by far not all. He published many other papers in the best journals, but they are not directly related to this topic. And he selected only those which related to his dissertation, although some other papers are also very valuable, and he did fantastic job during his study. Okay, then, any questions from the audience, please? Yes?
Yeah. Can you go back to your, and I remember you have a slide about the graph between GN, NM, and
Yeah.
The graph show time and something. So what is on OX axis?
OS?
OX 250,
yeah,
500. What is its unit?
Yeah, this is the dimension for the problem. And here, the problem here is
Oh, so it means like
yeah, is a problem. So here we have to consider the dimension n here. That means we consider from the 200 to 2000. Right.
also it means like you can find a solution in the higher dimension of space.
Yeah, but until now it's just about 2000, maybe 2 billion or 20 billion. So we still do it. We are still thinking about it because our methods now is very efficient in the case that we lower dimension like 2000, 5000, even 10,000. But for the case that is 1 billion, so have some trouble in computation.
And for your time here is what it is unit.
The time here, that means the time to conduct the numerical experiment, right? For solving one problem, like
Second, hour, or
second.
second.
Yes, sorry. I need to write more about it.
Yeah.
Second, not the hours.
Yeah.
More questions, please, from the audience. Okay.
I wanted to ask you about the function you sent to the further. You went to project. That one, I mean, where I can find it.
Okay,
Is it
there are
the-
paper of Federer from University of California, I think it's 1955, Federer.
It's in
And he was the leader of a big group in geometric measure theory. And then they developed something, they wanted to interplay between C2 smooth function and convex function, and then how I got familiar with this. Besides these topics, which I've been involved, I also involved in somewhat control problems for sweeping classes, in particular Chang here, which is one of the representatives of this group. And I dealt with Italian people there. And then, when I give a talk regarding proximity, those people say, okay, but it is well-known notion, because people use this in a dynamic system and whatever. And in this way I discovered for myself, and when I talked to Terry Rockefeller, he was amazed because he didn't know anything about it. And indeed this notion, formulated in an equivalent way, not exactly this one. And if you're interested, I can give you all reference. And now it's used by European people, mostly Italians and French. They use for dynamic system, and they did a lot of that's very interesting. I was very much. Okay, we can talk about
What
it.
kind of dynamical systems are you talking about?
No, they consider geometric measures here. Now it's actually such system is known like from Wasserstein space. Are you familiar with that? Right. That's what more kind of related in modern language. But they use beautiful geometric measure theory, developed this theory, and then it has been applied to evolution. That's what. Okay, any more questions, please? Okay, if no questions, we excuse all publics, all committee members, and
They stay here to have some lunch with us.
okay. If Phat will get the approval. Okay.
It's amazing, the winter, the air conditioning.
Okay, okay.
Summer, it's not.
Very nice to see you.
What a messed up My office is freezing in the winter, the one day of cold air comes in.
Oh, yeah. Mine too.
Very nice to see you. Okay, stay here.
I cannot believe it.
What, John, any questions?
I have a couple.
Yes, please.
Okay, let's start off with your main theorem has a positive definite condition on the Hessian, right? So how is that really necessary? I mean, can one sort of modify somehow the theorem to look at Hessians that are, maybe just semi-definite or something?
That's a good question. I found definitely answer now.
Yeah, so we can choose the direction we can satisfy in this condition. If we, because the Dam Newton method, classical Newton method require the positive definite, which is stronger. But here we can replace the Dam Newton method by regularize Newton method. Then in this case, we only need the positive semi-definite of the
Yeah,
Hessian.
see, what I'm thinking of is that you have certain directions where the Hessian is positive definite, and certain directions where it's negative definite. Let's assume it's non-degenerate, so there's no zero directions, right? And then maybe you could work along, maybe you can do something,
Yes, very good suggestion. Actually, what we did a bit different things. We modified, modified these methods, put some kind of, for example, like here. And in this case, we can use positive semi-definites everywhere. But what Professor Klein suggests is a very good idea. Even without any kind of regularization, to consider different directions. In one direction, we may have positive definites. In some other, we may not. And maybe we can move to this direction.
Now, we can do this because in some cases we can relate the direction by gradient descent.
Mhm.
We can gradient descent, but when we use in some iteration, and after that we have the positive definite of ascent, then we can show the term.
No, but it was not implemented. It has not been implemented.
Yeah, no, but just a
Right,
suggestion,
yeah.
maybe
Yeah,
there's something, you
I think it's a good idea.
generalize your theorem. The second thing I was thinking about, because I don't know about any of the applications, except I know something about least squares methods, is, economics, mathematical economics, you try to find equilibria, right? This might be a way of trying to find equilibria of some sort of problems in economics. Wouldn't that be like, you've done things like this before, right?
Yeah, I did, but in different framework. But it's
But
very
maybe
great
this is like a
question.
way to,
Right, yeah.
it could be applied in that setting,
Yeah,
right?
it's
I
good
mean-
idea. It's good idea, John. Right?
Yeah.
It's a great idea comes from you.
And then the third thing I wanted to say, now, none of you here except for me thinks about, I think about manifolds. I don't know if you know what a manifold is, but manifolds are patches of Euclidean space sewn together, right? And somehow you have to have, I noticed in your, things you wrote down, you need an inner product of some kind. You need like a Riemannian structure. Maybe it's not C infinity, maybe it's just C1 or C2. But like you want to do maybe some sort of variational analysis on these kind of C1 manifolds or something. Maybe there's a way to get out of Euclidean space.
Oh, that's fantastic, really. John, you have a lot of predictions. Just today I got a paper which is called Variational Analysis in Wasserstein Spaces. And they, develop some ideas. I didn't know these people, just sent to me, and European guys, Italian, French, but it's really great idea. Now it is in the round somehow. It started to do things, not much has been done, but there are people who are interested, and that would be really great. But you agree with Professor Klein, right? You understand, right? That what we do is Euclidean spaces, and we may do some kind of Hilbert, but it's still spaces with with linear structure. But there are some other spaces which you are familiar with where we don't have linear structure. And that's important for many applications. And that's indeed not much has been done. And today paper which I can send this paper to you, I was very much impressed. They use this kind of our constructions but developed in the case when we don't have linearity in the space. And
In some sense, what you guys are doing is very local. Because, in a manifold, locally it has this kind of structure,
Yes.
and you want to sort of globalize the idea to make it a global kind of approach. Right?
Yeah, even it's a good idea to start with Adamant spaces, which are the simplest probably among Riemannian spaces, and then to see. It's a good idea. Thank you very much, Jan. If you do something, we'll keep you posted, and you'll be our co-author. Yeah, why not? It's an idea came from you.
This was a very impressive. You did a very good job explaining your work. I think I don't see any problems on my end. Okay, so.
Thank you.
Yes.
What are your long-term plans? Do you want to stay in academia long-term, or
Yeah.
do you,
No, he got professorship.
I know, but that
Right.
doesn't mean he wants to stay in academia.
No,
Many
he's
people-
going to stay in academia, as
Excellent.
far as I understand, right?
Yeah,
And
that
he will
makes
make
sense.
some career, I believe,
Yeah, exactly. I will stay in academia for 1 year, for not 1 year, for long year. Maybe I will continue to develop some general and matter or some
Okay.
other projects. But at least maybe 5 or 10 years. Yeah,
And then, after 10 years, what was then?
I don't know, but at least I think.
Yeah, okay. I think as far as I know you, you
there's-
really belong to
I think there's potentially a lot of geometry in all of this.
Yeah, absolutely. Geometry teacher is the main. Okay, thank you very much, John. Then, any questions? Yes, please.
Yeah, I mean,
Repeat.
I also agree that you presented your work very well, very clearly, and it's also very useful work to have these usual methods extended to differentiable functions. So I mean, maybe sort of related to what John said, that you choose like this second sub-differential where it's more where it's positive definite. But so right now you don't have uniqueness, but can you choose which is like more positive definite, so maybe it's like faster gradient descent?
Yeah, faster gradient descent.
Because right now, say in the numerics, when you run this once, now there's no uniqueness. Now if you run it again, you'll have different sequence of directions that you can choose. But are they always consistently better than the other methods?
Actually, we understand
You just get lucky.
the theoretical aspect now. If we choose any direction, so we can
It'll
convert
converge.
it. Yeah,
It'll
but I don't
converge.
know
Is it
if we
faster?
choose this
Yes.
direction and another direction, one different. So
Right.
we don't know right now. But yeah, that is very interesting anyway. So we need to compare. If we choose this direction, so and if we choose that direction, yeah.
Actually, I just want to continue with John, Professor Klein and
You call me John.
But let's just move on, because your theory basically in the case you assume positive definite property, right? So I'm thinking, can you maybe in the future you can generalize to the minimax province, and in that case your function may not be that nice. So, because why I suggested this question is because in computer science there's something called the adversarial training method of GAN, right?
Yeah.
Generative adversarial network, right? That's very popular since 2014, right? So that's basically a minimax problem.
You say which kind of network?
Because GAN,
Right.
they generate images and models. Like there's the most famous model is this AlphaGo, right?
I see.
AlphaGo, they use AlphaGo to defend the Go champion, the Chinese Ko Jie in
I see.
2017.
Uh-huh.
And then that's fantastic job. So basically, the mathematical model is just min-max.
Yeah.
You first take the max, and then you take the minimum.
Mm-hmm.
In that case, your function may not be that nice.
Yes.
You want to solve for the solution, right? So basically, my understanding, you use Newton's method to solve for the zeros, right? So here, this minimax has a solution. Because I think maybe there's some way you can apply your idea, but with substantial modification, definitely. There's a different problem.
it seems to me like this is actually pure math, right?
Yeah,
But
but
it seems
with
like it
applications.
should have a lot of applications.
But there are some
There
applications,
should
but
be
it's
plenty of applications of this, because the idea is I mean, what are you trying to do, right?
Yeah.
You have a flow, you're trying to get to some stationary point, that's what you're trying to do, right?
You know, minimum, we try to solve some problems, and this is actually what numerical optimization.
Yeah.
Of course, what is behind is theoretical issue, you're completely right. But now it's some numerical issue, some application
Yeah,
which
yeah.
were not expected actually when, before Phat happened to be here, we didn't know about all this stuff, right? And Phat did a lot of good stuff.
When you
to
were
provide-
developing this like general type of calculus, right?
In more or less,
was
yes,
the, were the
application to
applications in the back
optimization.
of your head?
But not to numerical optimization. The
Uh-huh.
point is that what is really new and really fascinating, numerical
I
application.
see.
And when we have algorithms, then they can be applied to solve problems. We cannot apply to solve problems, from calculus and optimality conditions,
So you're gonna be
right?
talking to the guys in this corridor
Right.
eventually, right?
Yeah, that's, I think it's really great breaking through. And I'm very happy with that,
So
I
I
tell them
think
they can
it's
stop
this-
working on C2 functions.
Yeah, maybe you can get rid of Galerkin methods entirely, right?
I think
Yeah.
this minimax probably is a new paradigm you can work on. Maybe it's very popular. I mean, you need to. People still need to set up the mathematical theory, background, everything. So it's very hard in computer science. So it's deeper than
Yeah.
this problem right now. But I think it's very, very useful program.
Thank you for your suggestion. We think about.
Okay, indeed, thank you very much for all your views. And by the way, what about Professor Murat?
Is he
Alper?
on Zoom? Yeah.
Yeah, maybe he, okay.
You ask him.
No,
Alper.
no.
We have to end the meeting.
We end the Zoom
But
already.
he's on the committee,
Oh,
right?
he's on the committee.
He has to vote.
Yeah,
Yes.
but at the same time, I think maybe he has some questions.
Yeah, but now
Could
I
you
can-
please invite him?
Yeah, put them back into the meeting.
Right, but you may have to email and let him know to rejoin the meeting now.
But now I will add.
And only let
Only.
him join, that's it.
What?
Yeah, just,
Only give him permission to join.
because he will
Do you
feel
understand
discriminated.
how they hacked the meeting the second time?
So again, I think maybe someone got careless and that's some person in that it wasn't
Let's wait
legitimate,
for.
But maybe email him and let him know that, I mean, ask him if he can
Yeah,
rejoin.
just ask if he has any questions.
Oh, yeah, he's here.
Oh, he's here, right? Okay. Oh,
Professor, can you hear us?
He's
No.
connecting to
Yeah.
audio. Can't hear you yet. Where is he, actually?
I don't know. But he's not in Michigan, somewhere. Alper, are you with us?
Yeah.
Hello? Do you hear us?
Yeah, what is here?
Yes, Popper, I can hear you.
Okay, wonderful. Okay, thank you very much for your participation. Do you have any questions to Phat, please?
Sure. And no worries. I think the work is
Maybe.
We cannot hear you well.
Maybe you can
Sorry.
type in the chat box or
Yeah.
something.
Right, if you have, yes, that's right, you may type something, if you have questions.
Yeah, if you have a question, type it in the chat box. If not, we have to decide.
sure. I will.
Okay, good. Because it seems like your connection is unstable.
Right.
No, there's a chat. See the chat?
Check.
Can you hear me?
Yes, we hear you.
Yeah. I don't have any questions.
Oh, great.
Okay, wonderful, thank you very much again for,
Sure.
where you now, Alper, where you now?
I'm in Turkey.
Oh, I see, oh, a long time.
Yeah.
Long way from here. Okay, hope that you enjoy there,
Yeah.
right? Yeah. How's weather there?
Sure.
How's weather? Very hot?
Yeah. Not too bad, Boris. Not too
It's
bad.
not like here.
It's
Yeah.
warm. Yeah, not like here.
Okay, thank you very much indeed. Okay,
Sure,
now I
sure.
hope that you agree with us, that defense was good, right? And we can make decision now. Okay?
He needs to stay with us.
Ah,
Yes,
oh,
he
okay,
does.
oh, you
Stay
say.
with- So let's
Stay with-
make, let's make a decision. But he has to leave the room.
Right, okay, Phat, could you excuse for a moment?
Don't go too far.
Yeah.
So this is one of the better presentations I've seen.
Yeah.
Yeah, it's
Despite all
very
the
good.
pornography.
Right, I know,
Right.
Yeah,
Yeah,
you know, but why
but
did
his
it happen?
presentation
You
was-
know,
What?
why did it happen?
Somebody hacked the meeting, right? It was hacked.
No, well, the thing is, the link is public and
Yeah,
all kinds of.
that- we should not be publishing links public. What we should do is send out to emails to selected people from now on. It shouldn't be.
Yeah, I
public.
never
No,
seen
but
anything like this.
within blog puts it on the Wayne State main events.
Yeah, but we should not put the
Okay,
Zoom
so
link.
maybe-
If you're interested, email
Right.
the secretary of the map
Yeah,
department.
right.
Right.
Because actually I saw that he will invite only Chaim, but he invited more people.
Yeah.
No,
That's,
he gave
Permission
permission
to someone else
to
to
someone
present,
else. He
uh,
didn't recognize. He did that.
I see.
Yeah,
That
but
was
they
the
had,
problem.
but they had the link. That was
Yeah, they first
Yeah,
had the link.
they had the link,
and then
but then
he
also-
gave the instead.
Yeah, there are
he gave
people who
that
go
guy
around
the,
doing this, right?
Yeah.
permission.
Okay.
Yeah, there's some really disgusting people.
I know, that's so offending.
Yeah.
So
Anyway,
let's-
I say he passed with flying colors.
Yeah. I
Right,
think so
right,
too,
you know,
yeah.
he's a good guy.
Yeah,
Actually,
so
I think, you
I have
know,
no problems with the result.
yeah, I think it's,
You know,
from the sad part, he just broke up with his girlfriend of 10 years, and he was
Oh,
very
yeah.
much disappointed. But it's okay. It been a couple of months ago. It seems
Yeah, but he's a
that-
solid student. I mean, like,
Well, he's a good one, and he will be
yeah.
very good researcher.
Yeah,
Right?
I'm,
you know,
I'm glad we produce researchers.
Yeah, okay, that's I think.
Boris,
it's-
will you ask Alper what he thinks?
It's again.
Ask Alper.
Yeah, Alper, what do you have? What do you think? Do you have any opinion about Phat defense?
Yeah, I think he has done very good work for it. I mean, despite the interruptions with the Zoom hacking, I think his work has demonstrable contribution with publication. So I am voting. I vote for him.
Okay, thank you very much indeed. I think, you know,
Okay.
your impact is very important for many of my students, and I much appreciate your time, you know,
Thank you,
to be in
Boris.
the committee. Right. Okay, enjoy Turkey. Okay.
Excellent.
Yeah.
Which city are you staying right now?
I'm in Izmir.
Izmir.
It is on the west side
Yeah.
in the middle.
Yeah,
close to the
close, is that close to the historical site of city of Troy?
Troy.
It is to the south of Troy,
Ah.
but it is on that side of Turkey. It's on the west side of Turkey. Yes.
Yeah,
Yeah, Izmir is well-known place indeed.
yeah.
you know.
Yeah,
Of course,
yes.
of course.
Not less known than in Troy. We also have Troy here.
A lot of dates come.
Yeah,
from there,
exactly
dates.
right. Yeah.
Izmir dates, yeah.
Okay, that we could invite Phat, right?
Yeah. We have to congratulate him. Let's open up our presents.
Before we accept this.
Yeah, I know, but that's.
Otherwise, you gotta
Open up
secure
the
the
presents.
bribe,
Right,
right?
exactly, right, so.
No, it's polite to open up the presents, right? Well, we'll do it in a second. Okay, we think you passed. We're not sure. No, we're sure.
No, okay.
And I think this is like you probably opened up a brand new subject, right? It seems like.
Yeah, right. You know, that's really great. So I'm so happy to have had Phat as my student. And he definitely will continue his collaboration, his research, and you know, I believe that a lot will come out of this.
Thank you.
He's very active now. He's going to get green card soon, and will be travel to different places.
Excellent.
Thank you very much.
Okay, thank you, Phat.
Yeah.
You know,
Oh,
thank
wait,
you.
wait, wait. Where's-
You can open
The first week, there's something. First, when did you sign Dr. Mura?
Yes. Yes, okay, just thank Professor Mira.
Thank you for your time to provide me the opportunity to present my research. I appreciate that. I also prepared a present for you, reason for you, but I cannot give you now. But I will give you in the maybe next week or yeah, it's fine.
Yeah, and another thing, you need to have the title page.
Wow.
You need to give us all the including.
We have to sign it.
We have to sign that. We need to sign that.
We can do this over email, it's not a problem. Email.
Yeah, email and also the form. The form. There's
Oh,
not
yeah,
only
I
the
know
document,
it,
there's the
but
form.
Thank
Yeah,
you.
you need to get it
Yeah.
from the graduate school.
Yeah.
Ask the front desk. Ask either Bob or what's the name? I forgot.
T-shirt.
Yeah, Kishe, you know, ask the applicant, you know, to get, to download the form, and we need to, give each one of us. So we need to sign within a day or two.
Okay. Yeah, so you'll email us the forms and we'll sign it electronically. It's good.
Right, I think I got some form, even, 2 days ago or something.
Yeah, well, we'll just do an email.
And
It's
then
easy,
I
it's
said,
easy.
I think, but you can get the form, or you did not.
I just, they're electronic forms, those are
Yeah,
different.
electronic.
Those are different.
Okay, then I think it's.
Yeah, but the copy is physical, because we need to sign the basically like a physical.
Yeah, I will understand.
Yeah. Thank you.
Yeah. Congratulations again.
Yes, thank you, really.
Congratulations,
Very
Pat.
good.
Yeah, thank you. Doctor, do that.
Wish you all the best.
Yeah, thank you. Thank you.
Bye-bye.
Bye-bye.
Bye.
Bye.
Take care.
Oh,
Wow.
The photo with us.
By the way,
ah.
Izmir used to be called Smyrna. It was part of
Yeah, I
Greece.
know, I know.
I remember 100 years ago it was called Smyrna.
Yeah, right?
And well,
okay.
let's say it's thousands of years ago, right? That's in the history.
Vietnam.
Yeah, of course. Yeah.
Okay, I'll be right back. I have to go to the
We'll talk
bathroom.
more, right? No,
I'm
no,
sorry.
okay.
I didn't realize it was
We'll talk more, right?
Yeah, the discovery of Troy was a big event, by this German archaeologist named Schliemann, right?
Exactly, you're right.
Yeah,
You're right.
Schliemann strongly
Right.
believed
Yeah.
that
Professor, you can stay here and have lunch.
Right, but just remind me.
here, and then they spent a lot of time digging here, digging there. Actually, he dug out something older than they joined.
And where's Professor Clark? Where is
And they
John?
found that the most amazing thing is gold mask. They saw in the gold mask of Agamemnon.
Oh, wow, okay.
But it's not. It was the gold mask for royalty.